Hello, welcome to Berkshire Guitar Amplifier Repairs in Reading, England. Stuart Smith with you as always, and it's another Fender Blues Junior. This one has a hum which starts out sort of bearable and then over several minutes just gets louder and louder until it's not quite acceptable. So it's not a ridiculously loud hum, but it's definitely a noticeable hum. So I've got a couple of views on this. It could be the HT caps, one of those could be going. We can check that fairly simply. And there's another problem which I'm hoping it isn't, but we'll have a look. Anyway, let's power it up and see if we can reproduce this hum. Right, power on, and that's quite low level and acceptable at the moment. So I'm going to turn the camera off and come back in 5 or 10 minutes and see what it's like then. Well, here we are, literally just 2 minutes later, and already the hum is noticeably louder. Let's leave it a little bit longer. Okay, it's been a few minutes since I last turned the camera off, and I've done a few things. I'm afraid this is a problem. It's not the caps. It's a problem to do with the valve subboard here. So you may be able to hear that background hum. Watch what happens when I heat up the valve board. Can you hear that's got substantially louder? So this is actually a problem with the with this valve board being very slightly conductive. They've obviously used cheap fiberglass at some point, and the board is very, very slightly conductive. Right, so there's the hum, look, and I think it's round about this phase splitter area. I'm going to spray some freezer on it. Now obviously when I spray that you'll hear a huge amount of crackling and banging as the freezer conducts a little bit, but have a listen to what happens after that crackling is gone and the board's cooler. Much louder hum. Now still a bit of crackling from the freezer. That hum's gone down significantly just because the board is cooler. All that racket, of course, was the actual freezer acting as a slight conductive path between various tracks. So that's the situation with this board. And now there are a number of design features that are very bad on this board. Unfortunately, Fender didn't design this very well. So this is the area here that I've identified, which is sensitive. Now this is pin, let's have a look, 1, 2, 3, 4, 5, 6. So that is pin 6 there, that one there, which is an anode, so that's at like 230 volts. And this is pin 7, which is a grid, so that's at 0 volts. And look how they've run these two tracks here parallel to each other with this tiny, tiny gap between them. Really poor layout design, particularly as, look, they actually had room to take this track out here and round. And this area here has become very slightly conductive. We're probably talking, I don't know, 5 meg or something, or maybe even higher than that. But that's all it takes for that voltage to get across onto the grid there and cause that hum. That's not the only problem with these boards. They suffer from another major issue, and a bit difficult to show you, but it is, if I have to take the board out I'll show you. It's this track here which they run between these two pins here. This is pin 3. One of these tracks is at high voltage and one's at low voltage, and this literally arcs across here and just burns this board up completely. I've seen lots of boards completely destroyed by this basic schoolboy design error, not having enough clearance between a high voltage track and a low voltage track. The cure for this is we're going to have to take this board out, and I've got some replacement boards which I've just dug out. I'll show you those now and you can see what we're going to do. But it's a reasonable job to do this now. Here's the board that I bought online. If you I think on eBay, if you Google replacement valve board for Fender Blues Junior, you'll get this properly made, decent board, conformal coating. They've got around the problem with the track there, routed that track properly, and all in all this is a proper printed circuit board, the sort of thing Fender should have put in originally, of course. So our job is to remove this board here and replace it with this one, and hopefully it'll work. I've never done it before. It's my first attempt at replacing this board with a new one, and it comes with a bias pot, so we're going to add the bias pot here as well, and that allows you to measure the bias on these two test points, because at the moment biasing this amplifier is not easy. In fact, it's hard and silly. So there you go. Let's have a go at that and see how we get on. It'll be a first for me. Well, I'll just talk you through this. So we're going to take the valves out, then we're going to take out the 1, 2, 3, 4, 5, 6, 7, 8, 9 screws holding this board in. Then we're going to ease the board up this way. We're going to desolder all of these ribbons and then solder them into here, and then put this board back in there. Which way round does this go? That way round. So it's going to end up like that. So we're going to take this ribbon here under here, through there, and solder it there. Now, fairly tricky. We don't want to. These aren't particularly robust. These ribbons, they tend to break, and we've got a lot of desoldering to do. So I'm going to break out the desoldering tool on this one. And to remove this board, don't try and do it from here, the nut side. Get a screwdriver under here and undo it from this bottom side. But first of all, let's take the valves out. And this spring arrangement always falls apart the second you do this, so you may as well take that out at the same time. I'll leave that dangling, seems to want to dangle. Take the preamp valves out. Coming to the end of this. Right, that's the last screw out. Let's turn this back up and there we go. So I'm just going to have a quick measure to make sure there's no nasty DC voltages hanging around. I'm sure there won't be, and there aren't. We've got 6 volts on there, 12 volts on there, that's fine. Good, and so now we can start to joggly. What's this here? Okay. Oh yeah, we've got these heater wires. I've forgotten about these. These greens here are the heaters, which are going to the board as well. There. So in theory, this should shrivel up like that. Yes, it does. Right, I think to make my life easier, I'm just going to desolder these heaters here. I'll just use a bit of solder braid on that. One, two. That's the heaters out of the way. Now, with a bit of luck, This should, doesn't want to. There we go. Right, that's what we want. Okay. So that's the situation there. Can you see the burning around this board here? Look. That's the power valves getting hot. Right, now it's not particularly easy to desolder this because this kind of wants to be up like this to be desoldered, and I guess that's what we're going to have to do. Don't like bending these ribbons around too much. So there we go. Right, now I'm going to get the desoldering tool out, because if it was just 4 or 5 I'd use solder braid, but there are quite a few there, so let's get the heavy duty machine on the job. I use this Tool desoldering station. Very good and very cheap. I think it's about £100 if you can get them. This is the one to go for. You can spend a lot of money on a desoldering station, and it just has a gun like this and a vacuum. When you press the trigger, the vacuum sucks the solder up as well. Right, the soldering tool's up to temperature. Let's see how we get on with this. Looks quite good. Some of these are bent over. I'll bend those up before I desolder them. Okay, now I'm going to try and bend up the ones that are bent, because you can't desolder them. Or maybe I could just use some braid on those. Might be easiest. Right, now, how's that worked for the first ribbon cable? Yes, it has, with the exception of this bent over one, which is hanging on in there. There we go. Right, that's one ribbon cable out. Not quite sure the best way of doing these bent over ones. The second one will come out. Oh yes, good, that's 2 out, look. I've got 2 bent over ones on this one. Don't make our life easy, do they? Let me turn the desolder tool off. Okay. Yeah, there we go, that's the last one. Good. So that is the board out. Let's now have a look at the board. Right, here you can clearly see that problem track, look, comes along here with high voltage on, or one of these got high voltage on, goes between these two here, one of which has got high voltage on, I can't remember which, and this arcs across here and burns out this whole area of the board. Great design that, isn't it? Look at that. For a piece of rubbish printer circuit board design. Really, really poor. And then here's the problem area that we've got here. Look, that scratching down there, so I've run a blade down there to see, just to make sure there's no contaminants in there. So look at the clearance look at the clearances on some of these tracks. Look, there's hardly anything between this one going this way and this bent one here. There's nothing between these two. This is 1, 2, 3, 4, 5, 6, pin 6. That's an anode, so that's got high voltage on. And it's running dead parallel to this grid here, with virtually no clearance between the two. Absolute basic schoolboy. Yeah, I was making those mistakes when I was 13, laying out printed circuit boards by hand using tape and a razor blade. This is so-called professional design. Really poor. And then on this side we can see the burning of the board by the power valves here. And then anyway, there we go. So this is the replacement we're going to pop in here. Much better quality board. Won't suffer from any of those problems, and they've rerouted those tracks to be more sensible. Don't know, could that have been easily rerouted, that track? Let's have a look. Single-sided, of course, the board, not double-sided, so they needed to get from there to there. Well, I just think, do you know what I would have done? I would have just changed these pin layouts to have, if you shove them all up one, then this could have come around here into this pin here, maybe. Yeah, because that one could easily go into that final one. This one could easily go into the second one in. This one could easily go into the third one in. And this one, instead of taking it all around the houses here, just comes in here. But, you know, I don't know. Who knows? So now we have to get this board in, and it's just a kind of reverse procedure, really. I'm going to tidy up these a little bit. These are the ones that got you know, bent over, so they're a little bit messy, a little bit frayed. Look here. So I'll just tidy those up a little bit before I try and put this board in. I put the pot in. That just went in there. And that's supposed to adjust the bias. Don't know. We'll put the heaters into those two pins there, though. That's where we took those green ones from, these two here. Yeah, well, let's have a go. Haven't done this before. Before I put the board in, I'm going to move the furniture, these nuts here, from this board to that board. That's just a question of undoing these and transferring it from there to there. That won't take me very long. Okay, I've swapped the spacers here from this board to that board, and we're now ready to put the board in. Now the trick here is to make absolutely sure you get it in the right way. It'd be very easy to mess this up. So the board goes in like this effectively. This is the old one, obviously, and these have to tuck under here like this. So we're going to put them in here like that, and then we're going to roll the board over that way. Yeah, that's correct. I'm absolutely sure about that. Very embarrassing to get this wrong. So the reason you can get it wrong is on this board. Look, you could solder them there, and also you could solder them there. So you could make a big mistake here. Let me think about this. Really get this correct. So this has to go this way because it's single-sided. So it goes in there. In on the valve side we're going. And then we're going to rotate it over. And these are now going to be tucked underneath here, and put the board in so that the ribbon's tucked underneath here and comes up underneath there. So that's what we're going to do. We'll start with the first one. There we go. Not particularly easy to hold this and solder it, but it's okay once you've got one tacked on. So I'm just going to effectively just tack that on there. There we go. I'll come and do that joint again later, and then I will tack this one on too. Need 3 hands for this really. There you go, that's just tacked on. So now I can go along and solder those properly. One, 2, 3, 4. And then we'll just go over these ones that we tacked. And there. That's that done. Good. So now I'm just going to go along the rest of these and solder the other ribbons in, and then we can put the board back in. So now the next thing is to gingerly put this board back in. By being quite careful here. Like so. Cord knows if this will work or not. Suppose you've got to try these things, haven't you? I know what I need to do. I need to... yes, I haven't. That's a shame. Right, I forgot to put those heater leads in. So we'll just, I think we'll pop them in if we can, get them in from underneath. Good. Right, that's the heaters in. Pop this back in here now. Right, so now I'll just put in the screws that we took out earlier. Secure the board back in. We're fairly close to being able to give this a bit of a test. Right, I won't bore you with putting all those back in. I'll put them back in and I'll rejoin you in a moment. Right, now the board's in, the other thing that we need to do, according to the manufacturers of the board here, is to change that resistor there, R52, from 22k to 56k. This is to do with the bias circuit here, so I don't quite know how they've done the bias on this, but I'm just going to slavishly follow their instructions and see what happens. So that's the next thing to do, and I must also remember to put a cable tie around there. Not that it's particularly important, but I will do that. Okay, the moment of truth. You're seeing this as I'm seeing it. Board's in, changed the resistor, got a guitar plugged in, turn the reverb down, knobs kind of middling. I've got this meter ready because I'm going to quickly measure the bias in my old-fashioned way. Then I'm going to have a little look at how they do it on this bias pot they've added. But the old-fashioned way is to go between the red here. Be very careful because this is at 350 volts, and I go between the brown. And volts equals milliamps, so 2.5 volts would be not quite milliamps. 2.5 volts is 25 milliamps. So that's how you do that. Now so let's turn it on, see if it works. Moment of truth, see if the valves light. Yeah, valves are alight, that's a good start. Ooh. working. Nice. Okay, let's quickly measure the bias. I don't want it to be obviously running away at some crazy amount. So let's see. Oh, it's quite low. Look, it's 0.9. So we've got 9 milliamps, about 10 milliamps bias. That's okay. That's nice and low. And on the blue, it's 9 as well, 10. So that's great. So it's not getting overly hot or anything. We don't need to worry too much. Let's see what that's great. So that works absolutely fine, that board. I'm well pleased with that. Now they have these bias test points now on the board. So let's actually see what they're doing there in terms of what we're expecting to see. What we've got here. Let me show you. I've got a second board here. I bought 2 of them. Right. So here we go. Right. Okay. I thought they had 1 bias point per valve, so I was trying to measure across here, but basically it says bias test point 0 volts, that's where you put your negative of your meter, bias test point there, so that's where you put the positive of your meter. So let's try that and see how we get on. I'm not quite sure how they've scaled this. Let's just okay, yeah, so millivolts on your meter, and millivolts equals milliamps. Come on, 10 milliamps, look, which is what we measured, or nearly 11 milliamps, which is what we measured the old-fashioned way as well. Great. Now, the question is, does the bias adjuster work? Let's get my little trimmer. And well, I don't know which way around it works. Let's turn it up a little bit and see what happens. Unfortunately, it's not easy to turn whilst holding your probes on here. It's also quite easy to short your probes onto the chassis here. That wouldn't matter, but that's God, it's very hard to get on here. It's sort of like a domed piece of solder. Can't get good contact. 14. Okay, so clockwise is more bias. We'll work out the bias. I think it's usually about I don't know what it's 25 milliamps on these roughly. I think. Let me just check the plate voltage. So the HT 345 volts HT. So on a 345 volt HT, let's have a look at the. As you now know quite well, I use the Weber bias calculator. I always mispronounce that. And Ted Weber, TEDWEBER.com. Ted Weber, I think that's pronounced. And you just pick your valve here. EL84 already. What do we say? 350 roughly, wasn't it? 3,500. 350. Calculate bias. 24 milliamps. That's supposed to be there. So short-term memory loss. Did we say 350? I can't remember now. .342, that's close enough, yeah. So 25 milliamps-ish is what we're looking for. So we can tweak that up a little bit more. This is good, this works really well. Congratulations to the people who made this board. Go back onto milliamps again and see what we've got. .17. Okay. Turn it up a bit more. Come on. 32, that's a bit high. Come back a bit on that. .28. Maybe turn back a bit more. 22, 23. That's good enough. Perfectly alright, that's good. I don't like these things running too hot. Sometimes they run insanely hot, the L84s. They get slated a lot, these Blues Juniors, mainly because of their reliability problems and the various issues. You know, they have cheap electrolytic capacitors in them. We have this board issue. I had one in the other week which had completely caught fire. The entire board here was charred. That board there was completely charred, almost certainly caused by that problem I told you about. One or two other little foibles, but when they work, they are very nice little amplifiers, and I kind of recommend them really. The problems are well known and not particularly expensive to solve. Like, for example, I've been doing this for years, and that's the first time I've changed one of those boards. I've repaired a couple before, so it's not like it does it all the time. Yeah, so they're good little amplifiers, and I recommend them. Here's the board here, on eBay. Complete Fender Blues Junior FBJ tube valve PCB board with bias test points. That's the one there, look. About 20 quid. 19.95 plus postage, 23 quid or something. Very nice little product. Congratulations to whoever took all the effort to make this for us. I shall definitely be buying some more, and I won't be bothering to repair any boards anymore. I will simply swap them. Okay, so now I think we can put the back on the unit, and might leave it on for a half an hour just to make sure that board is okay. Now, just before I put the back on, here's another absolute newbie error by Fender. These are the 6 screws for the back. There's the back in place there, ready to have its screws put in. Do you notice anything about those? Yes, of course you do. This one's shorter. Now, my guess is, and it is only my guess because once these screws have been taken out, who knows, is that this short one here goes here, because a long one will go through and possibly impinge on some wiring or electrics further back here. That's just my guess, whereas of course a long one doesn't make any difference here on a corner or down here. Now, that is an absolute no-no. When I was designing electronic equipment, we used to employ a safety officer, an external company, to come and check my designs after I'd done them for safety, because safety is a very non-intuitive thing. There are things that you just wouldn't think of in a million years, but as a trained safety officer you know about them, so it's always wise to get someone else in rather than thinking, oh, I've designed that, I'm pretty sure it's safe. And the very first thing he would do would take all the screws out of everything I'd made. Sometimes there were 30, 40, 50 screws, and he would take the longest one. Let's say it was this long, and he would put that screw in every single screw socket that there was available, and see if it caused any safety issues, touched any live wires or inside or anything. Even if it was ridiculous, that screw obviously didn't go where he was putting it, he would put it there, and you can see why. Because if it's possible to do it, people will do it. And this is a good example. They've made that short for a reason. I suggest it's a safety reason, and yet it's very, very easy just to blindly go around putting all these screws back and end up putting this one in here. I doubt it'll cause a major issue, but still, that's another good example of what I would call amateurism on the part of Fender. Like putting 5-watt power resistors down onto the board, so that they char the board and the connections come undone. That sort of thing. It's just absolutely basic stuff. Anyway, I'll put these screws back in, and we'll power it up and leave it on for a little while. If you'll indulge me, I can't resist telling you a little safety related story. I designed a piece of equipment. Let's just use this as an example. Some equipment with displays and mains power inside, and because it was running reasonably hot, I'd put some ventilation slots in the top of it. Now these ventilation slots were really fine. You couldn't even get the tip of your finger in more than a millimetre, or even a child's finger wouldn't go in more than a millimetre. And beneath those slots was the mains transformer, which I hadn't sleeved the connections to, and they were quite a long way beneath the slots, so they were about that far down beneath the slots. And he looked at that, and he looked inside and said, "Nope, can't have that, that's got to go." And I said, "Why? Well, that's ridiculous. How on earth can that be not safe?" He had a real twinkle in his eye, this guy, because of course he'd seen it all, you know. And he said, "See if you can guess." And I said, "Well, you'd never get your finger in there. Even a screwdriver," which obviously, you know, you can't really protect against people shoving screwdrivers and things, but a screwdriver wouldn't have gone into it. They were very fine slots. I say, a little tip of a child's finger wouldn't have gone in. Nothing would have got in. Yeah, of course, water would have got in, but you can't really protect against water. And he said, "No, it comes from the days of television," whereas that's exactly what they did. At the back of the television, it had sort of fine slots to let the heat out. And ladies who wore long gold chains would lean over the back of the top of the telly to dust the back behind it. The chain would fall down through the slot, touch the very live parts in a television, and electrocute them. And they had, I don't know, a handful of deaths or whatever. And since then, that had become a safety issue. So, of course, it's highly unlikely that a lady wearing a long gold chain would lean over this, but that's not the point of safety. The point of safety is, if it can happen, it will happen, and you don't want to kill someone as a result of your negligence. So this is, you know, quite a long time ago now, and of course these days you'd have a very fine mesh. If you want a ventilation slot, you'd have an incredibly fine mesh there, which nothing could get into. Anyway, I thought you'd be interested in that. Okay, I thought it would be interesting to do some tests on this board that we've taken out, just to see if it really is conductive or not. So what I've done is I've set up some test points here with some bits of tin copper wire, look. So I've come off this area here, which we thought might be problematic. We've come off this area here where the track goes between those two, look, and I've got a connection on there, there and there. And I'm also going to go on to the heaters. So I need to add another one there. I'll just add another tag there so that we can check this heater track. Because look, this heater track is very parallel. Look, if there's going to be any conductivity here, the heater track will be the one that shows up the board conductivity. So I'll just add another little tag there. And then what I'm going to do is I can clip on my Mega here, and we can do some insulation tests. Okay, so the first test we're going to do is to clip on the heater tracks here. The Mega, by the way, I'm sure you know, but it puts out 500 volts DC and tests for insulation breakdown. You can't test insulation breakdown at low voltage, you've got to do it at high voltage. So let's see what this is like now by pressing this button here, and you can see it's got a very slight conductivity there. So let me zoom in on that. You can have a look. So what we're looking for, if you can get the light so that you can just about see the meter in between the fluorescent light. So as I press the button, you can see it's very slight. See that tiny slight increase in the meter? That should be 0, and that's reading 100 megohms, which is also a very high impedance, but it should be nothing there. So already we have a problem. By the way, I'm betting that this gets worse with heat, which of course we will do. So now let's check this. Now we're going to check the track that goes through these two pins here and is very close to them. Look, so I'm going to clip onto that one, and I'm going to clip onto that one, and then onto that one, and see what we get on both of those. Where's the other side of that gone? Press the button. Nothing at all. That's completely open circuit, as it should be. And now I'm going to go on to this one. Press the button. Not a flicker on the meter, completely open circuit as it should be. So at the moment there's no leakage on this track going through these pins. finally, let's check the area that we suspected on the phase splitter, which was these two tracks here that run quite close together. So let's see how they're performing. So I'll clip onto here. I'm just going to touch them together, make sure the meter's working. Yes, it is. Right, now I'll go onto here, press the button again. Absolutely nothing whatsoever, so there's no leakage there. Right, now I want to see what happens when we heat up this board. So I'm going to use my heat gun. I'm not going to go too hot, just you know, moderately warm to hot. We're going to do here. Alright, that's heated up the board a little bit. We're just duplicating the conditions where the valves have been on for a while and the board is getting a bit hot, so let's go back onto this one again. The area we suspected might be problematic, and the meter has gone up. I'll zoom in there. There should be no conductivity at all here. Again, let's get that so you can just about see the meter. Right, I'm going to press the button now. Look, 3, 2, 1, boom, and there you go. See that slight rise? Not very much. A couple of 100 meg. Let's do the same experiment now on our heater circuit. Our two heaters here, the heater tracks. Press the button and whoa! So zoom in, have a little look there, look. Pressing the button now. Whoa, look at that. That's 10 meg between the heater tracks. Should be open circuit. You can see the problem, can't you? And now finally, there we go, so we're on our two parallel tracks here. Press the button and no, there's not much there. Okay, so maybe it wasn't in that area, maybe it was some other, you know, leakage from the heater circuit. So so that's not too bad, that area. Let's try our I'm going to heat this up again. It's gone a bit cold. Let's see what happens now on our track that goes between the pins circuit there and there. It's registering pretty much what it was before. It's not 0, but it's not particularly high either. And try this one here. There's nothing there at all, so it doesn't seem to be a problematic at the moment, this board on here. Of course, once it arcs across, leaves a trail of carbon, and then it's like you've got a conductive path between the two. So at the moment, the main problem seems to be on the heater side. Okay, I've reheated the board and I've gone back onto this area here, the area that we originally suspected, and look, boom. So we were right, and that as the board's cooling, I can actually see that that meter going down. So I'll just heat it up again. And have a look at the meter. Sorry about these lights. Press the button. Dump. Whoa! And look at it falling as the board cools down. So that's yeah, 5 meg or something. So there's the problem. Look, that's between pin 6, which is an anode, and pin 7, which is a grid. So there you go. That's the problem. And I would quite like to see if this one fails. Let me just try this one again. So I've heated it up again, and I've gone between the track that goes through the middle and this one here, and look at the meter. We have 50 meg, so basically that is also giving a resistance look. Should be 0. Let me show you that a bit better. Should be 0. Press the button and it's 100. Actually, that was higher. The more I heat this up, look at that. As I take the heat away, it starts to fall quite dramatically. So you see the problem here. This is underneath one of the power valves, and you saw how burned it was on the other side. So this is getting hot. Let's try this other connector here. Now, that's not so bad. The other side of that pin doesn't seem to be. Well, I don't know. Yeah, it's not as bad, but heating the board causes the board to conduct. So all over this board, you have conductivity. It's conducting between these heater tracks. Look, they are the most continuously and in parallel. So all these leakages are adding up to make that you know, really quite bad. And then it's conducting between here and here, and here not quite so badly. And we are getting our conduction between these two pins here on that track there. So that's the problem. This board conducts electricity when it gets warm. Fantastic. Nice one, Fender. Love it. Well, I quite enjoyed that one actually, because that's given me another solution now for Fender Blues Juniors that have got funny valve board problems. I don't have to start hacking tracks and linking wires and stuff. And at £20, I think that's really good value. Just bung one of those boards in and you've got yourself a bias test point as well, which is excellent, because biasing these Fender Blues Juniors is not usually very easy. You have to cut out resistors and, you know, put resistors in parallel with other resistors and that sort of thing. So it's not great. And job done, amps working, really like it, and customer will be delighted, I'm sure, because he's been plagued by this for a long time. And I hope this also helps you if you are having hum problems on Fender Blues Junior. Don't forget, hum can also be caused by those cheap electrolytic capacitors, but in this case it wasn't. So that's it from me. I'll catch you on the next video, and thanks as always for watching.